So, Dr. Anand, sir, so shall we proceed with today's session, sir?
Yes, sir. Shall we start the session, sir?
Yes, sir.
Yes, sir. Thank you, sir.
So,
let me share.
let I give a small introduction, sir. Let I proceed with myself, sir, and just hand over to you, sir.
Okay, sir. Okay, sir.
So, good morning, all my dear participants. Um, on day one, for all your hormonal presence, we have three sessions on yesterday's FTP. So on day one, AACT sponsored ATAL FTP. We are having three sessions. For session one, we are having the inauguration, which is for this we have resource person Dr. Sankar Venugopal sir. He is vice president from Mahindra and Mahindra. On session two, we have having resource person Dr. Praveen Kumar sir for the topic of architectural design for EV. On session 3, we are having the resource person Dr. Lenin sir for the topic on electrical drives and its control. So we have all three wonderful sessions on yesterday's day 1 ATAL sponsored FDP. So with this same, I just welcome you all for this day 2 series of sessions. Now, on this day 2 for the session 4th session, it gives me an immense pleasure to welcoming today's speaker. So, Professor Dr. Anand is working in Professor Electrical and Electronics Department in PSG Tech, Coimbatore. He had his bachelor's degree in EEE from Pondicherry University, followed with post-graduation in Power Electronics and Drives from PSG Tech. He had his doctorate from Anna University in the field of special electrical machines. His research areas includes special electrical machines, power electronics, electrical drives and control, and energy conservation. He also has several sponsored research projects, journal publications to his credits. We thank him for accepting our invitation to share his views and thoughts. On behalf of the Department of Mechanical Engineering and Sri Ishwar College of Engineering, we welcome you, sir, for the program. And also, I just welcome all participants. So now the session is handed over to Dr. Anand, sir.
Thank you, sir. So thank you for the warm welcome.
Thank you, sir.
Let me share my screen. Sir, whether my screen is visible, sir?
Yes, sir. Your screen is visible, sir.
Okay, thank you, sir. So, respected faculty members, so research scholars, students, and the organizing team of this ATAL FTP. So, a very good morning to one and all. So, first of all, I would like to thank the organizing team for giving me this opportunity to handle a session in this ATAL FTP. So, I be a faculty with the electrical department of PSG. So, for the next 1 hour, maybe I can share my ideas about the e-vehicle systems, especially concentrating on the electromagnetic drive systems, its selection and requirements. So today is the second day session. So hope I think so we have been given very good basic knowledge on the EV systems, the type of the electric vehicles. So what are its impact in the current emerging scenario, and what are its impact on the energy conservations. So today I am my lecture section is something with respect to the energy conservation that you can able to adapt by designing a proper electromagnetic drive systems. maybe we should concentrate on a four-wheeler segment and a two-wheeler segment. Then we can make a conclusion. So what are the ideal hazards that should be incorporated in selecting a proper drive system? So the short agenda for this session. So we shall see about the various advancement in the electromagnetic drivetrains. So the specification, what are its requirements to satisfy the current industrial needs? So what are the key performance metrics that should be considered for a perfect electromagnetic evaluation of a drive system? Then we can conclude with respect to some of the case studies. So what we have done. So this slide, I think you can get a very good image of the OEM, especially with respect to the Indian automotive sector. So four type of variants we could see from three branded OEMs like a Tata, Hyundai, and a Mahindra. And we could see recent days that the Tata EV Nexon has taken prime importance even in the middle class family segments to take its drive. So let us understand with respect to what is the electromagnetic drive that is available in this kind of segments or in this kind of variants. The first one, as we know, is a Tata Nexon EV variant. The next one, the Tata Tigor EV variant. The third segment, Hyundai Kona Electric. The last variant, the Mahindra Electric e-vehicle model. So all have been successfully launched. So now, an interesting point, what is the drivetrain that is used as a prime mover in all these kind of variants? For the first variant, we could see the electromagnetic drive is a PMSM type. That's a permanent magnet synchronous type. For a second variant, we could see it has been launched again with a PMSM type. Now we shall see about the second OEM, Hyundai-based Kona Electric model. We could see that again the variant is a PMSM drive system. While we consider the Mahindra e-vehicle model and all the models of Mahindra, we could see it's a three-phase asynchronous squirrel cage induction variant. So that makes a point of interesting. So what is the electromagnetic drive that should be compatible maybe for a four-wheeler segment? So the choices in our Indian automotive well-proven scenario so narrows down either to the PMSM variant or to the asynchronous variant. Maybe in future we could see some other type of variants, maybe a cost-effective, maybe that is an alternative to the PMSM variant and the induction variants. The grand comparison of how the topology or how the electromagnetics came into picture. Initially for traction, we used even the brushed AC series motors. But when it comes to the EV segment, due to, as we know, the commutators and other some hazards in the brushed motors, we thought of initially going for an induction motor. As we know, a Tesla initially launched the EV segment vehicle with a three-phase asynchronous induction motor. Then why today, even in the four-wheeler segment, even in the two-wheeler segment or a tri-wheeler segment, the research more they concentrate on the magnetic motors. Maybe the induction variant cannot be able to give a high power density, high torque density within the limited volumetric constraints, even though it can able to offer the induction variant. a very maintenance-free operation, a longer life with less noise and vibrations. So all these some minor disadvantages are overcome by the magnetic motors, which can able to offer a wide range of speed control at a very less volumetric constraint. That is, the torque yielded by a BLDC motor, what we call a PMSM, as the name indicates with respect to the electromagnetic EMF, what we produce. If it is a sinusoidal EMF in the air gap, what we say it is a PMSM. If it is a trapezoidal, we say it is a BLDC. So the excellent power density, the torque density, and the compact size and volume makes the OEMs to shift into the magnetic based drive systems instead of a conventional asynchronous drive systems. So the option left in the earlier scenario, so we have been with respect to the brushed motors, then we have been with respect to the induction motors, and now we can see even for an Indian OEM, we could see down the line, almost the PMSM variant is a proven concept. But maybe some disadvantages which include the cost of the magnet, as we want to depend upon several factors which makes the magnet more costly and its price becomes more volatility, so which makes all the research engineers to think about a motor which should not have any copper, which should not have any magnets, which should not have any aluminum bars. The rotor should be as less weight as possible, maybe within the same volumetric constraint, the diameter and L, leads to the emerge of a new concept called the reluctance machines. Even though at present commercially launched reluctance based EVs in a four-wheeler segment or in a two-wheeler segment is not practically available, maybe the next 3 to 5 years down the line, we may see some of the reluctance motors driving the automotive sectors. So what we call the switched reluctance or the synchronous reluctance. So normally the saying is when we go for a reluctance, the power factor will be very less, the saliency ratio will be very poor, but with the advancement in the power electronic modulator and drive constraints, so we can able to achieve a very good power factor and a very good saliency ratio by opting a very good control by using maybe a FOC type of controls, field-oriented type of controls. So the machine configuration is the first point, how we can start the design of our electromagnetic drive systems. So in this session, so we shall see something, a general layout, maybe for the next 1 hour, pertaining with respect to the designer's choice when it comes selection of different parts covering the electromagnetic drive system and what are its basic requirements. So the first designer's choice may be to land up or to start up with what is the machine configuration. So can I go for a PMSM drive system with the rotor which should be placed interior or which should be placed exterior. So what is the type of the magnetic configuration we should inbuilt in the PMSM drive, and how the different stator, what we call the stationary part, and the rotor, how they geometrically defined with respect to the volumetric constraint for the given D and L, how we can configure the machine. That's the first designer's choice. The next one, For a perfect electromagnetic drive, we need a complete optimization of the stator core and the rotor cores. Stator core is a crucial point where you are going to accommodate the total ampere turns, which determines the maximum electrical loading your machine can able to withstand. Whereas, if you consider the rotor core, it defines the core structure, or in other words, we can say the maximum flux yielded per pole will be deciding your magnetic loading of the machine. So unless otherwise we make a good choice of electric and magnetic loading, it will be very hard to get a driving torque from the PMSM drive. The next constraint of a designer's choice comes with respect to the D&L fitted with respect to what is the choice of material we could use. Can I go for grain-oriented steel, or can I go for a non-grain-oriented steel, or can I go for a CRGO type of steel? Even a 2 to 3% efficiency in improving your drive system at the overall can able to increase your range coverage of the entire EV system. So that's another designer's choice. Then comes your rotor design. As we know, the PMSM drive system is implemented with an array of magnets. What kind of magnet we can use? What will be the purchasing capability power? So which type of configuration that can yield a high flux density within the limited main frame dimensions? So that's again a challenging designer's choice. Next comes the stator winding. Can I go for a concentrated winding, or can I go for a distributed winding? Or can I go for a winding instead of a round copper coil, instead of the traditional copper coil? Can I go for a rectangular copper bar segments where it is bounded at the overhang portion? Again, this is a designer's choice. The last one comes with respect to a power modulator. Because today we speak about the different charging topologies. So basically we convert the AC into DC, and we store the DC in a lithium-ion batteries, from which we use the traction inverters to obtain a variable voltage, variable frequency to produce a perfect electromagnetic drive systems. So what should be the compatibility? In later slides, we could be able to see that even a composition change in your power semiconductor devices can be able to drastically reduce the size and the weight of the traction inverter, which is a very good advantage for your e-vehicle to increase or to enhance your length of run. So let us see in a general view the factors influencing the selection and what are its basic requirements. So this image, as I said, the two particular variants dominating the EV electromagnetic drive system, the asynchronous induction machine and the PMSM unit. So as you could see, the rotor of a asynchronous induction machine consists of a short-circuited copper bar by means of the entrance. Whereas, if you consider the rotor of a PMSM drive, so here you could see how the magnets are available in the rotor core of a PMSM drive. Here you could see the rotor, here you could see the magnets, 1, 2, 3, 4, 5, 6 magnets, forming the 6-pole configuration, which are kept buried or inserted into the rotor core. Now the designer's choice. should I go for an inserting magnet or should I go for a magnet outskirt of the rotor core? Maybe we will try to analyze several OEMs that will be that have been into the EV market, starting from the Toyota model, and we can get a clear idea what is the designer's choice for selecting and what are the requirements when we design a rotor of a PMSM drive systems. And it is proven that the D and L, as long as maybe if there is a small fluctuation or if there is a adaptability with respect to small extension of the D and L, even low cost magnets like a ferrite can able to achieve the torque densities when comparing to the higher end magnets. So that's a very good advantage when compared to the existing, the asynchronous induction drives. The first point, whether it's asynchronous or of a PMSM, the electromagnetic drive system, the first thing starts or originates with respect to what is the material, what we use for our rotor core or for our stator core. So in the picture, so here you could see some of the rotor core options. So in the left hand side, you could see the core belonging to the reluctance type, and in the right hand side here you can see some of the core belonging to the PMSM types. So this core material, so normally we say it is of iron based material, and proper selection of the material, its composition, its thickness and its orientation, everything will play an important role in enhancing the overall efficiency of the drive system. For example, so here you can see I have given some composition of the same of 5 different laminations. So here you could see sample A, sample B, sample C, sample D, sample E. So the major component present in this lamination material of the stack is going to be a iron. So here you could see the composition. On an average, it comes around nearly, on an average, for example, 97%. We can do a simple spectroscopic analysis by taking a small stamping, maybe of 26 or 27 or 29 guard systems. Then we can find out the metallurgical compositions that is available in this stamping. So normally there is a saying that higher the presence of silicon in the metal stamping will have a chance of reducing the yielded magnetic flux density, which in turn will reduce the specific magnetic loading of the machine. Also, this composition is directly proportional to what is the core loss the stack will be or the drive will be exerting when we exert the drive at, for example, at a line frequency of 50 Hz. So here you could see a difference in the electromagnetic property of the machine under 2 different variants, a 26 gauge system and a 29 gauge system. What we say traditionally, so with respect to the ASA standard, so we say the different lamination stacks ranging from M15, M19, M22, etc., M47. So we could see the core loss that is available for a 60Hz component and a 50Hz component. For example, here you could see for M15 grade of metallurgical composition, which comes at a 26 gauge, which is a 0.47 mm thickness, the total core loss exerted per kg comes around nearly 2.93. But if the same material, M15, if you go for the 29 gauge system, which comes at a reduced thickness of the stamping for a 0.25 mm, you could see that the core loss at the same 50 Hz component drops to 2.53. Even though we say that high efficient energy motors, for example, now we speak about IE3 and IE4 instead of IE2 and IE1. How this energy efficiency can be accommodated, especially with respect to EV systems. In EV system, the electromagnetic drive system, if you are going to make a small change or incremental change, even with respect to the lamination material, it will be having an adverse effect in reducing the core loss component of the drive, which means that your efficiency will be directly increased, which means the torque handling capability, your specific peak power handling capability, everything will be on an enhanced level. But they may be saying that maybe the cost of the materials when we go for a low core loss will be on an increasing way, but when the volumetric goes up, automatically the cost per kg will be a reasonable one. So this is one factor. So now we could see that several standards arise with respect to the different gauge thickness for the materials available for the drive systems. So we have the JAC standard, we have the IEC standard, we have the European norm, we have the ASTM standard. Okay, so everything compatible or focusing on the type of the steel, as we use the non-grain oriented type of steel sheets for getting the optimized flux density in the drive systems. The next one, why we need a variety of reasons for selecting an electromagnetic drive. What are the reasons or what are the requirements? It comes from different corners. A few corners maybe we can address. Maybe there should be a proper selection of the magnet. There should be a proper concern of the soft iron material. As we discussed, the lamination is nothing but a soft iron material by yielding a very less core loss, maximizing the power density, flux density. And even we can concentrate on small subsystems involved in the powertrain. Example, the encapsulating materials, which we use for isolating the proper conductors from the iron core or the non-magnetic sleeves. And even we can think about the role of the static switches for our drive system. As I said, even a small variant in the structure of the controlled devices can be able to enhance your power density. So basically, the trade-off, even though there are variety of reasons comes into picture, the first trade-off in the electromagnetics of the PMSM drive comes with the rotor configuration. There are a variety of rotor configurations depending upon the designer's choice to be played exactly compromising the application and your requirement. As an example, here you could see the structure of the electromagnetic drive. The motor, the rotor consistent of a magnet, and we could see that over the rotor, the magnet is placed what we call a surface magnet type, and you can see the shape of the magnet is an arc in nature. This may be suitable, maybe in future slides you could see some of the applications and which OEMs adopt which kind of configuration based upon the requirements. The second one, the same SPM, maybe we can think about a breadloaf type of magnet, where you could see some taperings along the edges of the magnet. And this tapering obviously will be, no doubt, it will be introducing a reluctance between the higher reluctance between the stator and rotor in the air gap. But again, it should be considered as a designer's choice. Third one, the magnet with the arc shape at the inset type of profile. Then an exterior rotor, where the rotor, normally we say the stator is outside and the rotor is inside, but we can say in some type of configuration where do we require or mandatorily we require the rotor configuration should be the outside and the stator will be the inside, and the rotor can be of a what we call the arcium or the arc-based SPM types. Or even the rotor, if it is inside, we can think about the magnets that are with respect to a spoke type, which are inserted or kept buried inside the rotor. Or we can think about a V-shaped magnets. So this picture will give you the different kind of options in doing the electromagnetic analysis for the powertrain for your e-vehicle application. Now the choice, can I go for a SPM type or can I go for an IPM type? That is nothing but a magnet mounted on the rotor or a magnet buried inside the rotor. It is very easy, we can say that I can go for a SPM type of rotor where you can easily place the magnet over the surface and you can make a thick bonding adhesive glues for holding the magnet with respect to the rotor surface. But what is the problem? The speed range is going to be a limited one. If there is a high speed, if there is a temperature gradient exponentially increasing, then maybe wear and tear that will be making a problem with respect to the adhesive glue filling displacement. Maybe that may be leading to breakage of the magnets. Maybe we can avoid by using outer copper-based sleeves, magnetic sleeves, for a mechanical and a thermal protection. But the trade-off lies between what is the application we are going to choose. On the other hand, if you go for the IPM type of design, so here you could see a single stamping. So maybe it is a 6-pole rotor stamping where you insert a magnet segmented inside the rotor. It may be an excellent choice in compared to an SPM, as the magnets are kept safely buried inside the rotor. You can enhance the rotor speed to a higher speed. And also, interestingly, you can see that the air gap will be reduced by if you go for an IPM type of configuration. If the air gap is reduced, the reluctance torque will be overcome to having a shorter air gap will be reduced. At last, we can yield a higher flux per pole, which is a very essential in designing an electromagnetic system without losing the core saturation point. Now the choice. So when I can go for an exterior rotor drive or when I can go for interior rotor drive. So here you could see in the slide, there are two variants. Both are for two-wheeler segment. Both are the PMSM drive systems. So in the left-hand side here, you can see a motor, which what we call a hub motor. So here we could see the wheel of the hub motor over which we place the tire, the mechanical rim of the hub motor, inside which the PMSM motor is available. So it comes with a volumetric constraint. Your D diameter of the wheel is going to be constrained by the two-wheeler manufacturer. Your L, the length of the L stack length. So the length of the stack length of the motor is again going to be a constraint. So within the volumetric constraint defined by the OEM manufacturer, we want to pack our torque density. We want to pack our power density within the specified D and L volumetric constraint. So here you can see that we can go for interior stator with an exterior rotor for this kind of application. For example, if you see a mid-drive system, for example, here you can see the same PMSM drive. The drive PMSM motor is coupled with respect to the two-wheeler by means of a gear train mechanism. In this kind of system, it is very advantage. We can go for the exterior PMSM, and within the exterior PMSM also we can think about the IPM type of rotors. With IPM rotors, with magnets available inside the rotor, we can think about the efficiency improvement in the PMSM drive systems. Now comes, so what type of magnet that can be compatible or we can suitable for designing your electromagnetic drive. So normally, as we say, either a four-wheeler segment or a two-wheeler segment, for e-vehicle, so normally we stick with respect to 4 variants, either the samarium cobalt or the neomagnets, what we call the neodymium, iron boron, the alnico, or the ceramic. Now comes the important task: what should be the designer's choice? Can I go and select a magnet that has a very high magnetic strength, which means high magnetic energy? The energy product of the magnet is very high, which means that the flux per pole yielded will be very high. Second option, what should be the operating temperature? For example, if you see in the drive systems like this, even in a hub motor and in a mid-drive system, roughly the maximum temperature rise we can able to understand is going to be maximum 80 to 90 degrees Celsius. So should I invest a magnet that should be compatible, that's anything greater than 100 degrees Celsius for an e-vehicle application? Definitely it is not. And the third parameter, should my magnet should be a corrosive in nature? If there is a corrosion, maybe we can get compatible magnets, and we can have a protective, what we call the thermal potting over the magnetic grids, then we can implement for the system. The last factor comes with respect to the cost. As you could see here, the first prime importance of a designer's choice is not the corrosion, but it's the magnetic strength. The reason your D and L are going to be constructed. As you could see from this picture, the D and L, since are going to be constrained, we can't think about different variant of the magnetic grades, since we are going to compromise the electromagnetic compatibility. Next comes the temperature, which is also not more or less crucial when comparing to the EV applications. Obviously comes the magnetic cost. And we could see some of the OEMs, they stick with respect to the samarium type and the neodymium type. And even recent researches are available. Why can't alnico or a ceramic ferrite can be compatible to the existing magnetic grids? To understand this scenario, we want to think about what is the prime thing that the magnet has to be considered for selection for a e-vehicle. We say the DOM, that is the direction of magnetization. It should be towards the thickness or towards the diameter, or it should be radial in nature, or it can be multipole magnetization. Conventionally, we think about the existing types towards the thickness, diameter, etc. But recent researchers concludes that even a multipole magnetization will yield a high flux density, enhancing your electromagnetic torque handling capability of the drive system. So this is a pictorial image. So here you could see a hub motor. So the magnets are placed inside. This is exterior magnetic rotor. The magnets are placed towards the axial length of the stack length. So what is the type of magnetization flux lines that should be designed for the optimal thing? So let me show you a case study, or let me show you a thing that is observed from a branded OEM. For example, a Tesla e-vehicle. So here you could see the Tesla e-vehicle, what we call the Model 3, comes with a stator and rotor. Stator consists of 54 slots. The rotor comes with a 6-pole configuration. But here we can see, so this is the 1, 2, 3, 4, 5, and 6-pole rotor configuration. So there are several interesting points that you could observe with respect to this rotor pole. The first thing, if you observe the magnets, even though we say plainly it is an IPM type of magnetic drive, so we could see that it is not a single magnet. So here you can see several slotted magnets are bonded together to achieve a single magnetic arrangement, and that's what we call a Hall-Batch kind of magnetic arrangements. So what is a Hall-Batch kind of array? Instead of conventional inserting a single magnet inside a single rotor slot, So maybe we can have an inside view of this Tesla e-vehicle rotor core. So here you could see the segmented magnets. So this is what we call a Hall patch. So what is this Hall patch? It's a patented technique which consists of several kind of magnets which are magnetized using the magnetizer equipment, such that the flux lines yielded will be crowded and concentrated towards the stator tip to yield the optimized flux density. So here you could see, So here you could see the different type of segmented, a 4-segment magnet forming a single pole magnets. And if you could see from the electromagnetic analysis, so here you could see the different segments produce a concentrated field of orientation which are thrown into the stator teeth towards the stator core. Thereby the flux tubes what we get will be getting enhanced, and which results in an enhanced flux density. There is also researchers in the drive system. Why can't we think about a different granular orientations within the same segment of magnetations, within the same Hall patch kind of arrangements? So here you could see two kind of rotors. So here you could see the exterior rotors and the different kind of orientations. The flux orientation, the flux concentration may be with respect to 45 degree or a 90 degree. Put together, the flux oriented towards the stator core will be yielded at a higher point. This is not the only one observation what we could see from a leading OEM like a Tesla. We could also observe several electromagnetic changes what they have done in the rotor drive system. Interestingly, you can see that we say this is going to be the rotor stack length, and we could see that the rotor stack length is not made up of a single stack. We could see this to be maybe a stack number 1, this could be a stack number 2, and this could be a stack number 3. So we could observe that stack 1 and stack 3 almost equal in nature with respect to the stack length height, but stack 2 is almost higher when comparing to the existing top and the ground stacks. And also interestingly, we could see that the orientation of all the 3 stacks is not going to be equal in nature. We could see the stacks are shifted, what we call the skewing. It may be step skewed, maybe for different, we don't know, some different angles. Theoretically, we say that step skewing of a rotor will be reducing the cogging torque produced by the drive system. And even we don't know about what is the different kind of laminations for different stacks, or whether all the lamination stacks are made up of the same materials or different bonded materials. But 2 major observations go for a multi-granular polarization of the magnetic model. Second one, we can think about a step skewing in the drive system, everything to do almost to get a pure sinusoidal back EMF in the air, as well as to get a very less SNR, that is what we call the noise and vibration values. And also we could see that the rotor shaft as a hollow shaft, which is something has to be considered when comparing to the rotor inertia of the drive systems. So these are the designer's choice when it comes with respect to the magnetic constraint of the rotors. Can I go for SPM or can I go for an IPM? In an IPM, whether I need a Hall-Patch array of different degree of polarization of the magnets or different step skewing of the rotors. So everything comes as a designer's choice. So to put in a nutshell, the various selection requirements for your magnet, for example, I have shown the new type of magnets, is several parameters may be listed. The top parameters, depending upon the load length plot, we can say what is the temperature handling capability, what is the maximum energy that you can get from a magnet, what is its maximum saturation point, what is its purity temperature. Then comes your cost. Of course, we can't compromise the cost with respect to EV applications since we go for samarium and neo type of magnets predominantly used by several OEMs. But still, when comparing to the torque and power density, the cost is a vital factor. Then comes your mechanical strength. As we could see that IPM is somewhat difficult in manufacturing and to, for example, to insert different polarized magnets into a rotor core, we need a good mechanical strength to prevent the breakage of the magnets or to provide a high mechanical strength when the rotor core is operating at high speeds. Now comes the next important selection of the electromagnetic drive, the stator core. Normally we say the stator core houses your entire ampere turns, your entire flux linkages that are produced by your windings, which are the balanced distributed windings in the stator core. So in a nutshell, we can say that the selection of the total number of slots in your drive stator is going to be a crucial thing in the overall design of your system. So the design of stator slots is directly proportional, or it should be a critical designer's choice when we think about minimizing the corking torque, minimizing the pulsating torque, of course, a noise-free operation. So in fact, several authors, as you could see from this slide, several literatures are available for selecting an appropriate stator core for designing a perfect electromagnetic drive for a PMSM drive systems. We can also refer, for example, the PMSM design book by Professor Hendershot, which gives a clear design strategies to obtain a perfect stator or rotor pole configuration for the electromagnetics. For example, I will show you the different kind of slot per pole combination that we use for several OEMs. If you take a Toyota, or if you take a Tesla, if you take a BMW, or if you take a Tesla older version of the induction motor model, and if you take all the branded OEMs, each adopt their own stator slot per pole configuration for these kind of e-vehicle segments. So let us try to understand in general, so what should be the few requirements for a proper selection of all these materials or of all these variants. The first one, how we can select the total number of slots. Can I go for example, a 20 slot machine or a 30 slot electromagnetic drive, or it can go for 40, 50, etc. There may be some thumb rules or defined electromagnetic rules that may be considered in selecting a proper drive system. Maybe due to time constraint, let us see in short. There is a rule number 1. Here you can see the x-axis defines the total number of the poles and y-axis defines the total number of the slots. Which combination which can use for our electromagnetics? The first thumb rule says, or the first defined rule says, you go for a slot per pole combination which should be equal or greater than a point called 0.5, which is a well-proven concept to reduce the unwanted link flux leakage in linkages. For example, if I go for a 3/12 configuration, it is a proven concept that this rule is not permissible to select a slot per pole configuration of this combination. So here you can see some yellow regions which are passing the rule number 1 to select, or the first step in determining this slot per pole combination. The second rule, which is a resultant of the first rule, says that in order to get rid of the unbalancing cogging among the 3 phases of the machine, you select the HCF, highest common factor, for the slot per pole combination, then you stick with that result. So here I have shown you the case study. Maybe I can share you the PPT at later time. So here you can see that for a slot of 18 and 6-pole combination, whether it is advisable we can restrict with respect to this combination for the drive design. And the yellow shaded regions are the one which are passing both the rule 1 and rule 2 criteria, so which are taken over to the third step and the final step of the slot per pole as per the combination, which says that if you want to go effectively reducing the calling torque, we go for a direct LCM of the final slot per pole combination. So here I have shown you the case for the 6 combinations. So this is a key step that a designer's choice for e-vehicle application, the choice comes at this stage. Maybe we can have a very good selection of a lamination material, maybe a magnetic material, maybe a magnetic orientation, maybe a core orientation, but the number of the rotor cores and number of stator core slots per pole is going to be a paramount importance for the designers in the e-vehicle applications. In a nutshell, we can able to summarize that higher the total number of the slot per pole, normally it will be reducing the flux per pole combination. It also reduces the back end thickness of the cores, and the tooling cost also will be at the higher end. So we want to have a trade-off, the combination by deciding the winding layout, by generation of the spatial harmonics, by considering the carving torque of the drive system. We want to make a trade-off in selecting, or by considering all these things as a requirement for our drive system. So these are some samples what we could see from the leading OEMs. For example, we could say drone motor on an average comes at a 12 slot per 14 pole. You can see interestingly the rotor pole is higher when compared to the stator poles. You can see a Toyota Prius 2010 e-vehicle model. The electromagnetic comes at a combination of 48 slot or 8 pole. For a two-wheeler hub motor taken from the Indian OEM market segment, it comes at a 54 slot by 60 pole. Tesla, we have seen the Model 3 segment. The induction motor, which Tesla launched a successful model, comes at a 4-pole configuration, asynchronous type. If you take a BMW i3, i8, you can interestingly see that just a 12-pole rotor configuration will be yielding the required torque or the flux densities. The last one, the another combination, an 18/16 from the motor. Now the next point, should I limit only with respect to the slot per pole? It's not like that. As I said from the earlier, the D and L, the volumetric constraint, plays a very crucial thing in your electromagnetics. Because the drivetrain, for example, if you take the evolution of the Toyota drive system starting from 2002 until we could see here in the image, and I think a 2018 model, we could see the several stator rotor combinations, especially pertaining to the D and the L. So here you could see a 2002 model, the stator stack length, which is obviously less when compared to 2004 model, and 2010 we can see the enormous thing that has done in the electromagnetics of the drive to get a very less enhanced. Of course, we are sticking with the higher overhand position. So this D and L should be a constraint in also in selecting your proper S bar P of the drive system. So so these are some of the other combinations. So to make a idea about this D and L constraint with respect to the magnetic grades and the S bar P combinations. So here we could see a typical case study. For example, it is a two-wheeler motor, what we have done the case study for a mid-drive system. So here we done with respect to different slot per pole combinations, and also the effect of the magnetic grades have been taken into consideration. So here you could see the first figure 1 says a 12 bar P with a neo combination, neodymium iron boron combination of SPM type rotor. The second comes with a 36 bar 8 combination with a ferrite type. The third one comes with the 48/8 combination with the neo combination, and the fourth one comes with the 12/10 with the spoke type of ferrite. So flexibility is given with respect to the magnetic grade selection, flexibility is given with respect to the SRB, and flexibility is given with respect to the rotor pole orientations. But only one thing, we could see that the frame size, which defines the D and L of the motor, is not altered. It is made as a constant. And we could observe that on an electromagnetic simulating platform, the back EMF generated for all these four combinations. We could see a neo type can able to give almost a sinusoidal. Maybe some optimization should be required for the thing, almost sinusoidal. Like we could see some paths that is available in the peak point. But even though the ferrite can able to give sinusoidal EMF at the air gap, at the back EMF, but we could see a resultant of nearly 10 volt, the neo can be able to comfortably deliver for the same DNL constraint. For the same DNL constraint, the neo combination gives a higher back EMF, which may be resultant in a high torque density for the same specified DNL. When comparing to the NP characteristics, the speed torque characteristics of all these four combinations, as we could see from this slide, even a ferrite can able to give an extended speed range, but the torque yielded, we could see the torque yielded is almost 25%, a roughly value, which is a less when comparing to the neo combinations for the same DL constraint. But if we study the electromagnetic part, as we could see from this slide, the flux density distribution, both for a neo type as well as for a ferrite type, we could see the rotor, stator, and the entire electromagnetics is available within the core saturation limits. So we could not see any hot spot and we could not see any cold spots. Sorry, hot spot available entirely in the magnetic as well as in the stator cores. But the torque yielded is going to be of paramount importance, which cannot be compatible for the same D and L for as a ferrite magnetic state. In conclusion, a small case study. If you want to achieve the same neo type of torque density, where the neo ferrite lacks the neo with respect to 25% of the dimensional volume for the same D and L, it is mandatory to increase your D and L constraint, provided you are having a constraint with respect to a D and L, such as maybe for this cannot be, this condition will not be incorporated for a hub system, hub drive system, hub direct system. But if you construct an e-vehicle, maybe for a belt-driven, a mid-drive system, if there is a chance, for example, 10 to 15% of the active core length of the stack, L-stack material, L-stack length, then there is a combination. Because you are going to come at a ferrite when compared to a neo, where the cost performance will be very less or very competent when comparing to the neo families. So the selection depends upon what is the requirement. For example, if I want to select a magnetic material with a high grade, for example, maybe the case study what we have discussed, you want to parallelly think about what is the requirement, what is the demagnetization. If I think about maybe an interior, exterior orientation of the rotors, maybe we can think about the flux sinusoidal distribution at the air. If you want to think about my selection to be a high RPM rotation, we want to think about the inertia of the rotor, we want to think about the noise and vibration of the rotor. If you want to have a reduced cogging torque, a reduced losses, then we want to think about the core lamination of the electromagnetic system. At last, if you want to think about the manufacturing cost for e-vehicle segment between a neo type or a ferrite type, depending upon without a volumetric D and L constraint, we may landing about the cost. So last, maybe we can think about as a designer's choice, the overhanging portion, how far we can effectively reduce the overhanging portion as we know that the overhanging portion, as we could see in some of the things, the overhanging portion may be able to have a flux loss, what we call the leakage flux, which reduces the overall efficiency of the system. So these are the constraints for proper selecting of each and every individual part of the PMSM drive, PMSM motor, and what are its associated requirements to satisfy a successful EV drivetrain. Last, we want to land up a perfect design, what we call the A, B, and C, the specific electric loading, the specific magnetic loading, and C, how the type of the cooling, because if you go for a hub motor, we can't think about a liquid cooled, or we can't think about any other kind of driven system. You want to consider about the thermal conductivity of each and every materials, even for the peak torque and peak power handling capabilities. Coming to the power modulator. As we know, a drive is nothing but a combination of a power modulator and the electromagnetic actuator, what we call the motor. Can I go for a square wave drive, or can I go for a sine wave drive for e-vehicle segment? And its literatures are available with the proven technologies. A sine wave drive can able to enhance your drive life cycle, because as we know, the drive cycle of e-vehicle is subjected to different scenarios. So depending upon the drive cycle, we can select a sine wave drive which can able to compatible maybe for SPM type of rotors, or it can be ITM type of rotors, maybe a distributed, or it can be a concentrated type of windings. The power modulator of the e-vehicle, so just I have shown you block set, starting from the charging point, your infrastructure. So we convert an AC into a DC, so which is stored in a high voltage lithium-ion based batteries. Of course, we have the power factor correction units for improving the overall charging point power factor. So from HV lithium-ion batteries, we do go for the inversion by using the traction inverters. From the traction inverters, we supply a variable voltage, a variable frequency to drive the electromagnetics of the PMSM drive system. So several researchers are concentrating on several parts. For example, maybe a battery management system, or maybe a proper appropriate selection of the controllers, or maybe a DC to DC with isolated or non-isolated topologies. Now, as far as the EV vehicle segment is considered, when comparing the block diagram for the power modulator, we could see from the DC link, maybe from a high voltage DC battery, we convert into a variable voltage into a variable frequency by using the power modulator stage comprising of the control switches, what we call maybe the IGBTs or the MOSFETs. And more importantly, for the PMSM drive system, we use the rotor position conditioning systems. For a PMSM and for other kind of reluctance, it is mandatory that without knowing the position, rotor position of the hub motor or the PMSM drive system, we can't able to commutate the status of the controllable switches in the power modulator. From the rotor position controlling system, we do develop our own control logic to find the minimum inductance position, the aligned inductance position, the unaligned inductance position. Based on that, the control logic is generated maybe based upon a lookup table to generate the PWM, which are given to the gates of the controllable switches by using the PWM drivers. So for this kind of rotor positioning system of the PMSM drive, we go for implementing the Hall-based sensors in the stator winding of the PMSM drives. It is placed at particular mechanical degrees which can able to sense by using an IR transmitter and receiver using the PCB circuits, that we can able to detect the position of the rotor, which is then used to fire the controllable switches of the IGBTs. Now the recent trend in research or in e-vehicles concentrates on what is the type of the material that we can go for, maybe a controllable device, or we can go for a power semiconductor device, which are acting as a freewheeling components. For example, maybe for a two-wheeler segment, what you could see from this slide, implementing a MOSFET-based driver controls, can I make any change with respect to the semiconductor materials? Recently, we have been sticking with respect to the silicon-based devices, but recently, especially for the e-vehicles applications and several branded OEMs, now they have been thinking about the WBG-based devices, the wide bandgap-based devices. So maybe a silicon carbide, gallium nitride, etc. Of all these models, the silicon carbide model is a well-proven power converter substrate which will enhance your efficiency by implementing the PMSM drive system. So let me show you a small change, a research done by the ROHM when they go for the, I think, Europe formula race, even for designing an e-vehicle. We could see that a tremendous cost, weight, size reduction in designing the drivetrain by simply adopting the technology from a silicon-based controllable devices of the drive to the wide bandgap devices, such as silicon carbide-based devices. So here you could see the 200 kilowatt drive system, which initially originates at 15 kg, comes to with use of a hybrid using a silicon and silicon carbide-based hybrid module, where they can reduce a 2 kg per weight and 19% reduce in size. The next season, when the research has been evolved with implementing e-vehicle completing with respect to silicon carbide-based modules, stacks, they could able to achieve a 4 kg reduction in the season 2, season 3 model and a 30% reduction in size. Put together, the generic change what they can able to achieve from a silicon based to a WBG based silicon carbide based drive module, a total overall weight reduction of 6 kg, 43%. A similar thing you could see from the other side of composition also. What is its role in the drive topology? If you are going to constrain with respect to the drivetrain, any decremental cost that you are going to achieve with respect to the power electronic modulator, your control circuits, your weight, your cost, at the overall end will be going to an advantage by increasing the range covered by your e-vehicle system. Even down the line, it will be interesting to see, maybe down the line, maybe 5 years, maybe, we could see the WBG based stack modules, inverter modules, the DC to DC converter modules, which comes at a higher power density within a small D&M volumetric constraint, yielding a high power density. And even interestingly, we could see the the ripple free, the THD free components that can be as a part of these embedded modules. So put together, let me summarize in a nutshell. So what are the parameters we to select for a perfect drive and electromagnetic actuator for a PMSM drive system? Some of the parameters are the peak torque, the continuous torque. As we say, normally we design a system for a continuous torque system. For example, maybe I'll show you. So this is the NP pattern for a BMW i3 e-vehicle, where the continuous torque here you can see to be a 250 the power rating, but the peak torque may be substantially, maybe a 50 to 60% higher when comparing to the normal torque. So definitely for 0 to base speed or the corner speed, we want to go for a constant torque control. And beyond the base speed, we want to implement a field weakening control. And it has been several literatures are available. If you drive an e-vehicle drivetrain entering into a field weakening region, it will be a paramount importance where you can go for high energy conservation by minimizing the total power drawn from the drives. The peak torque, the continuous torque, your peak motor efficiency, your peak power, the coolant temperature available in the drive, the D&L constraint, your weight, your DC bus voltage, at last your degree of protection. So several OEMs bound their product with respect to their IP models, the ingress protections, which are defined by a several set of standards, protection against solid, liquid, gases, with respect to the environmental condition in which the drive is used, and with respect to what is the type of application, even a small vibration, all kind of things should be considered with respect to the IP protection. So to summarize in a nutshell, just I listed out only 6 key performance metrics which consolidate the requirement, the specific peak power of the drive system, the peak power density, the specific peak torque, the peak torque density, the efficiency of the motor at the peak load condition, of course. The last one, the cost. So the different strategies in a nutshell today what we have discussed for a perfect electromagnetic drive system may be summarized in a single flow chart. Either you can go for a reluctance or you can go for a PMSM type of motor. Maybe we can have our own decisions in selecting our topology. Maybe an axial configuration or a radial configuration or a different type of rotor saliencies, different type of magnetic steel compositions and combinations, different type of magnetic arrangements such as a Hall wedge or individual array. Maybe you can think about coiled wires or rectangular wires. Maybe we can think about the cooling and encapsulation. The encapsulation is nothing but, as we could see even in recent e-vehicles, if you see the anatomy of the electromagnetic system, it is completely encapsulated where the rotor slots and the stator slots and the stator windings are not being exposed, completely immersed and encapsulated by use of high temperature resistant potting. Maybe the temperature comes into picture. We can think about the magnetic with the low ambient temperature, but with the encapsulating condition will be a better choice for the EV system. At last, to summarize, the system trade-off of an electromagnetic drive system is a trade-off between 3 design teams, from an electromagnetic team, from a traction inverter team, from the mechanical transmission gear design team. Because we could see that if I concentrate on the constant torque region, the copper loss may be dominant. If I concentrate on the constant power region, maybe I have to sacrifice the iron loss. So it's all a trade-off between what is the maximum yielded flux density, what is the power density that you can be able to stack within the defined volumetric constraint D&L, and what is the frequency at which we are going to design the entire power term. So the designer's choice ultimately comes with respect to any FEM based models. The FEM models will be a right choice for selecting the appropriate design by considering all the things so far we have discussed. The electromagnetics will give you a complete picture. What will be the stator flux, induced flux densities in the machine? What will be the flux density per pole available? What will be the current density available? What will be the efficiency available? So here you can see the efficiency map available at various range of speed torque characteristics, either in a constant torque region or in a constant power region. So what can be the, for example, if I want to consider a base speed of 600 RPM, what is the maximum torque that I can be able to yield, for example, at a 20 Newton meter at a 600 RPM. We can also go for a wide electromagnetic analysis with FOC type of control by varying the lead angle control in the electromagnetics to software, such that in real time, these lead angles can be used in the drivetrain to achieve the same desired electromagnetic characteristics of your electric motor. Last but not the least, this drive system, we can able to analyze the hot spots, the cold spots, where you are going to overload the machine, whether the teeth is overloaded, or the magnet is overloaded, or the core is overloaded, or whether the shaft is overloaded. Depending upon the modern predictive control available for this kind of electromagnetic suits, we can able to perfectly match the alternating drive system with respect to the electromagnetic drives. So before we conclude, let me say maybe I shall take a small few seconds since we are running out of time. Maybe in the near future time, we could see about the electromagnetic drivetrains, which consist of a different variety of motor. Maybe it may be successfully launched in the coming years, what we call the reluctance drives. The main advantage, as you could see from here, the reluctance, maybe either it can be a switched reluctance drive, or it can be a synchronous reluctance drive. The stator almost, not exactly, almost similar with respect to induction and the PMC drive system. The rotor, we can think about absence of magnets, absence of copper windings, copper bars, commutators, end rings, aluminum bars, etc., which will be having a very high influence on the rotor inertia. But the only drawback, as far as the power turning drive is considered, the power factor. But even till today, not in an EV, maybe you can consider the industrial grade motors. If you consider the branded OEMs, for example, KSB type of manufacturers, it is well proven that the IE4 kind of efficiency is achievable even in synchronous reluctance motors. Maybe in future we can think about a PM assisted type of rotor configurations, maybe where we can think about by increasing the saliency ratio of the rotor and by using appropriate FOC control of the drive system. Maybe this can be compatible when comparing to the different magnetic grades, as we know that the magnetic becomes a very volatility with respect to cost, and we depend, since the indigenous and also the manufacturing issues with respect to the machinability of the magnets, inserting the magnets into the machine. Maybe in long perspective, the Singar may be a viable choice for the vehicle electromagnetic drive. So thank you one and all. So I think almost we are running out of time. So thank you for the given opportunity. So let me take maybe for a few seconds in completing the session. So if you have any queries or clarifications or anything, yes, you can drop our mail to the mail IDs. So we are happy to have joint collaborations with the faculty members and even the research scholars. We can take the cutting technologies with respect to the electromagnetic drivetrains at PST. So thank you, sir. Thank you.
Thank you so much, sir, for the wonderful session, sir.
Thank you, sir.
Sure, shall we take questions from participants, sir?
Yes, sir.
Right. So participants have posted some questions in chat box. So the first question is, what are the methods to avoid misalignment or bearing problems? There is question raised from Mr. Magesh Kumar, sir.
So misalignment in the bearing problems.
Yes, sir. Misalignment or bearing problems. What are the methods to avoid misalignment or bearing problems?
Okay, sir. So maybe one point with respect to the machinability of the bearings. So normally we do the type of the ball bearings for the EMSL drive systems. So we do consider the impact of the rotor inertia in considering an appropriate drive system. If the rotor inertia maybe is not going to be compatible with respect to the total payload available at the either end of the drive shaft, that's going to be a changeable thing, which may think of change in the eccentricity of the stator and rotor alignments.
Yes, sir. Sir, actually,
And also another point, when we do the electromagnetic simulation, if we think about the temperature effect on the bearings, it will be very much important. So we have faced one kind of issue when we develop the high temperature motor. When the temperature increases, there is a friction that is available between the ball bearings available at the shaft. At a longer run, we could see the eccentricity of the entire rotor profile has been changed. So that also may be an consideration.
Thank you, sir.
Okay,
sir, as we are running short of time, we are going for another couple of questions, sir.
Okay.
Sir, what are the challenges and opportunities for aluminum air batteries?
Aluminum?
Air batteries, aluminum air batteries.
Sir, to the best of my knowledge, I think I'm not sure about that thing.
Okay, sir. Okay, sir.
In our e-vehicles, normally we use a lithium-based one. But recent cutting technologies are available with respect to the battery management systems.
Yes, sir. Yes, sir. Sir, we will proceed with the next question, sir.
Okay.
Sir, the next question is, electrical vehicles are an important field of research at present. In that case, is it possible to have collaboration with such industry? If so, what will be the challenges from academic institution in such case of collaborations?
Yes, sir. Maybe I can take a few seconds about the facility what we have, sir, in our academic institution.
Yes, sir.
Okay. So, as you could have asked an academic collaboration. So, in our PSG, so maybe I can say a few seconds. So, we are having a center called PSG Center for Electrical Machines and Power Electronics. So, which concentrates on the electromagnetic designs, especially for the e-vehicles and industrial grade motors. So it is run by a team of faculty members and research scholars. So we concentrate on the energy efficiency motor, industrial grade, and the e-vehicles. So these are some of the type of motor drivetrain what we have developed along with the OEMs and the universities collaboration. So maybe we can take joint collaboration, the facilities what we have, and we can think about the. So these are some of the products what we have developed. So maybe we can think about the joint collaborations from the academic institute part in developing different kind of cutting motors for the EV applications. So this may be acting as a forum where we can use our joint collaboration where we have been exposed to different kind of OEMs. So this may be one thing, sir. Apart from that, so we have several R&D sponsored projects by different government agencies, which can also be an insight for this problem.
Yes, sir. Sir, thank you.
Sir, I have one more question,
Yes,
sir.
sir.
Sir, is there any advanced methods to control speed of a motor, sir?
Sir?
Is there any advanced methods to control speed of motors?
So as far as the power modulator is considered, so we are having the speed control precision, whether it's based upon a sensor-based technique or whether it is a sensorless based technique. Now, the advanced technologies what we use is a sensorless technique by using the state estimation instead of depending upon the conventional IR-based sensors what we mount in the stator of the motor. So by predicting the current and voltage and frequency patterns available to the stator winding, we can do a model predictive control and we can adopt a sensorless technique, so which is a recent thing that is available in the power modulators stages.
Okay, sir. Thank you.
Thank you,
sir,
sir.
one more question, sir.
Yes, sir.
Sir, could you tell me any difference between traction motor or and ordinary motor, sir, or both are same, sir?
So normally we define the motor with respect to the efficiency standard. For example, IE1, IE2, IE3, IE4.
Okay,
For
sir.
a traction motor, for example, if you take a e-vehicle, the total full load torque is available even at the rotor when even it is under the standstill condition.
All right.
When the rotor RPM equal to 0, the total torque available at the shaft of the rotor is going to the peak torque, and at the peak moment, for example, the motor design requires within a start of acceleration of 3 seconds, we want to achieve the peak torque density. So then only the vehicle can move, or then only we can able to achieve the movement of the vehicle. But in an industrial grade motor, maybe after reaching a 25% rated speed or 50% of rated speed, we can able to safely achieve the torque density and power density. So the traction motors involves achieving a high torque density, high power density within a fraction of time how far you are going to accelerate the system. So that's the reason we have discussed today. At 0 RPM, I need a constant torque control. At 0 RPM, I need a peak torque. So that's a major trade-off between in designing a torque capability when comparing to a traction motor and an industrial motors. Even for a two-wheeler e-vehicle system, the same thing holds. Even at a 0 RPM, we require a peak torque at that instant.
Thank you, sir.
Sir, thank you so much, sir. So,
Thank
as
you,
we are
sir.
running short of time, we will close this question session. Participants, if having any kind of questions, you can post your questions through SAS mail ID.
Okay, sir. Thank you, sir. So,
Sir, I request participants to kindly give your feedback. It is posted in chat box. Sir, shall we wind up the session, sir?
yes, sir. Sure, sir. So
Sir, okay, sir.
Thank
Sir,
you
at
all.
this juncture, I just thank our fourth session research person, Professor Dr. Anand, sir, for accepting your invitation and sparing his time to give a wonderful session on drive control selection and requirements. We are very much honored to have you in the session, sir. Thank you very much for delivering the session, sir.
Thank you, sir. So I thank all the faculty members, students,